In this video, we'll look at a calculation using a titration curve. So we have 50 milliliters of hydrochloric acid of unknown concentration titrated with 0.1 molar sodium hydroxide. I can answer number one a couple different ways. If I notice that it's hydrochloric and sodium hydroxide, that should be a strong acid and a strong base. Or maybe I would look at the graph. If they didn't tell me the identity of the acid and base, I could look at the equivalence point, which is halfway in the middle of that big jump, follow it across, and if the pH is 7, strong acid, strong base. Could it be a weak acid, weak base? It could. If they had very similar K values, then yes, at the equivalence point, it could be pretty neutral. Then often you might see the pH start a little higher. So instead of starting at like 1, maybe it would start at 3 or so. And instead of ending way up at like a 12 or 13, maybe it would end like around a 10 or something like that. But in this case, if I know the identity, it's got to be strong acid, strong base. A good indicator. I could just look at that indicator chart from earlier in the study guide. I just want something that's going to change colors around a pH of 7. Or again, if they gave me the Ka values, I want the opposite log of the Ka, the pKa, to equal about 7. So on this indicator chart from earlier in the study guide, we could maybe use that bromothiamyl blue. We'll just say BTB. That's kind of my favorite indicator. It's the one mentioned earlier on that titration curve. It's yellow in an acid, blue in a base, and the transitional color is green. So it's an easy one to use for titrations. You kind of know when you hit the equivalence point. Other options might be like litmus. Litmus is on this chart. If this were on the AP test and they gave you a chart of indicators, there would really only be one appropriate indicator. Okay, so now the calculations. How many milliliters of sodium hydroxide are added at the equivalence point? If we were doing this without a computer, that's when we end the titration. So if I were using this bromothiamyl blue, I would stop mixing acid and base when I see the green color. Now if we're using the computer, excellent. We can just go the entire burette of sodium hydroxide, and if I follow that equivalence point all the way down, I can get the volume added at the equivalence point, which, I don't know, do you want to kind of estimate like 23? Maybe like 23 milliliters of sodium hydroxide? All right, so then here's the beauty of a titration calculation. Often we want to figure out the concentration of an unknown. It could be the acid or the base. So we mix it with the opposite solution until we hit the equivalence point. That's when I know, that I've hit the ratio in the balanced equation. So we have the known solution. You have to know one of the concentrations. I know it was 0.1. Yep, 0.1 molar sodium hydroxide. That's moles per volume. It took 23 milliliters, or 0.023 liters, to hit the equivalence point. So if I cross multiply, I would have about 0.0023 moles of sodium hydroxide. At the equivalence point, I should reach the stoichiometric ratio between acid and base in the balanced equation, which sometimes you might want to write the balanced equation. With this one, I'm pretty confident it's a 1-to-1 ratio. Sodium hydroxide reacts with hydrochloric acid. It's kind of like a double replacement. In a neutralization, you should always get water as one of your products, or HOH. And the other is some kind of an ionic salt. Sodium chloride, it could be sodium nitrate, something in this case neutral. Now, we kind of mentioned earlier, just be a little careful. What if that would have been like calcium hydroxide with 2 hydroxides? Then when I reach the stoichiometric ratio, it might be like a 1-to-2 ratio. between hydroxide and hydrogen. But this is 1-to-1s, so I'm pretty confident then that I should have 0.0023 moles of acid. Because again, that's kind of the definition of being at the equivalence point. So now let's say we want to figure out the molarity of the unknown hydrochloric acid. Because it's a 1-to-1 ratio, I've got 0.0023 moles of HCl. 1-to-1 ratio. 1-to-1 ratio. From the balanced equation. And then you'll always know how much acid you started with. That will just be something that we measure in the lab. They tell me that there were 50 milliliters of acid, or 0.0500 liters. So all I have to do is plug that in my calculator, and I would get about 0.046 molar HCl. There we go. The concentration of the unknown. You can use the graph to figure out the volume of base added to reach the equivalence point. If you know the molarity of the base and you know the volume, you can figure out moles. And then by looking at the ratio in the balanced equation, you can figure out moles of the unknown. You'll always know the volume of the unknown, so you can figure out the concentration. Piece of cake. The last thing they want me to do here is sketch a little graph of this experiment, or a little setup. What would this look like? Okay, so I would have a burette. Here's my burette. It's perfect. It's not crooked at all, right? Here's the little trigger. And then down in the bottom, I would have a flask. There we go. They might ask me to label things, or maybe they would give me a sketch. That is kind of a wonky looking burette, isn't it? They might say where would the sodium hydroxide go? Or where is the solution of known concentration? The sodium hydroxide would be in the burette. That's always the known solution. The known concentration. Then the unknown goes in your flask. So in this case, it would be the HCl. That's my unknown. Because then we can measure the amount of base that it takes to reach the equivalence point. We can measure it using the graduations on the burette. The other thing that we should mention is the indicator. The indicator would go down in the flask with the acid. So we can tell when we hit that transitional color. Or if we're just using the computer and a pH probe, we should see the full range of colors for that acid-base indicator.